This is a Morisiki NGX 1000 SCM. It's our newest machine. It's some of the highest technology available in this segment of machining. There's 3 on the West Coast and we have one. The first thing we're going to demonstrate is high-speed PEG tapping. We're using a little bitty 632 tap to tap 455 stainless. And we have to PEG tap because it's about 4 times diameter and it'll just break taps and it's all kinds of trouble if you don't do that. We used to do this in 7 ops. Now it's 2. The spindle time is relatively the same. It's about an hour for the total spindle time, but we're reducing 6 setups. And setups is where all your time is, hours and hours of setup. This part is actually for a defense contractor that we do some work for. It goes in a forward-looking infrared camera. It's actually the resolver that moves the camera up and down. And it's 455 stainless. We're going to do all the holes on this side. We're going to tap this feature. Then we're going to do all the holes on this side. So it's going to do these holes on this side and the other holes on the other head. We'll go ahead and demonstrate the tapping. This is ER. This is something we use on about 90% of our tapped parts. It's responsible for really good finishes. And we'll just shoot a little of that in there. That's got a 76 tool magazine here. It's going to that magazine and grabbing a tool. It'll come down. It'll actually rotate the spindle to orient it. And this is the part I'm talking about, the PEG tapping. It goes in about 4 leads and then backs off to keep from stressing out and breaking the tap. But it actually taps at 2,400 RPMs, which is smoking fast. It's going to stop. It's going to rotate this side down. Now this is on 25 degrees, so the head rotates to 65 degrees to make 90. And then it'll just run in there and repeat the same process on the other side. The biggest problem we had with these parts before is we'd have to run multiple extra parts because we couldn't make a run of these without having broken taps in the parts. With this particular process, we can use 1 tap and make 100 parts. Now the upper head is going to rotate around. It's going to go get a turning tool. There's the turn tool. That's the roughing tool that roughs out the profile of the part. And it'll come down. And as you can see, right now it's facing off any extra material that would be there. When it pulls out, it leaves a little stop. It's going to rough turn everything +5. All the features that it can reach. This is the lower turret. The lower turret goes in there and roughs that out. And that's just insert drilling to remove a bunch of that material. It's a lot faster than milling it out of there. It's going to go grab. This is a drill that drills on center. It's a coolant drill. This machine has high pressure coolant, which allows us to do this heavy drilling with no pecking or anything like that. We have excellent chip removal, 2,000 PSI coolant. And what it's doing is it's actually pecking down in there. It machines in, then backs off to break the chip, then machines in, backs off to break the chip. And we do that so we can wrap our radiuses on down into that feature without plunging into extra material and damaging. Very small tools, so 30, 40 thousandths wide. When you set this up for the very first time, like this part, it took quite a while to get all this stuff to work together. It can be quite a big investment in time, but it pays for itself once the part's up and running. Every time you run an order of these and you shave 20 hours off the total throughput time, it's worth that initial investment. Our niche market is what other people don't want to do. That's, what's a tough part to them is our bread and butter, and what's impossible parts to other people is tough parts to us. See, what we're going to do now is we're going to grab another turning tool. We're going to go over on this head. And see, this particular, the surface it's machining is a datum surface, so that has to be parallel with the other surfaces. The tolerance is 1 thousandth of an inch, but really you got to hold it in about 5/10, or you have other related features that are hard to hold. And we take several passes here. We take the majority of the material in the first pass, then we take another light pass, then we take a final pass. It's only about 1.5 thou, and that's to take a nice fine cut and machine that good and parallel to the next surface. And this particular material, 455, is nasty to machine. It's tough, it's hard to break a chip, It's high strength, it's hard on tools, it's abrasive. Having the best tooling available makes all the difference. The best machine, the best tooling, the best possible support is what's required to make a profit on a part like this. It's difficult to machine. That's why we're doing it. It's actually going to go in and bore on the ID now. What it's doing is this a rough bore tool that roughs out all of the interior profile of the part. The tight 625 bore, the thread major diameter, the larger diameters, it roughs all that out. This is removing the majority of the material that's left. And then it'll actually come in, it'll do several other operations, grooving and threading. Now this is the finish bar. This actually puts our nice finish on there, brings everything to size. It's repeating the same profile, but at about 2/1000ths deeper. That's going to machine the ID thread relief. There's actually a groove in there that we thread into, so we can put our chamfer on the back of the thread. The idea is to get this part off here with as few burrs as possible. So we try to do about 95% of the deburring as we machine the part. It's threading now, it's single point threading. It's going in there and cutting threads. And then it'll come in with the thread tool one more time to remove any burrs that are left on the thread. What we're doing right here, this is actually kind of exciting. It's C-axis rotary pocketing. It creates all the radii and the features in the part and never moves the head off wide. This right here is a roughing op. I know it doesn't look like much, but that's about 7 thou per revolution on that drill, which is extremely heavy in this material. But it just runs and runs. The tooling is excellent. The high pressure coolant is what makes this operation possible. So that drill has holes all the way through it, and we pump 2,000 PSI coolant down the center of that drill to disperse the chips. That way we don't have to pull out to break the chip. We don't have to pull out to remove the chips. We just plunge it all the way in there in one pass. And what this is actually doing is drilling a hole so we don't have to enter slowly with our end mills. We can just plunge in there and cut. See, these are the end mills we use. They're sticking out a pretty good length considering their diameter. And they're relieved all the way back behind the cutting flutes, so we can go down in here and we can cut without dragging on the wall, because if you have flute for that entire length, you have chatter problems, poor finish, and poor strength. These are like Ferraris and Porsches and Bugatti. This is a top of the line, and for the parts we do, there's no other way really to make a profit than the best tools, the best equipment money can buy. This is the finish work for the inside of the part. That's all roughed out now, and as you can see, we move right along with that. It's probably hard to see on camera, but there's actually tiny chips being removed. That's the pressure that's applied to the tool. You can see it looks almost like powder coming out of there. What we're doing here, this is more the deburring we're talking about on the part. It's actually going around the outside profile with a tool with a 45-degree angle on it, and it's removing all the burrs and putting a nice chamfer on all of that. And there's no way you can accomplish this by hand, have it look as good and even double the time. It's not possible. And this is to achieve, continuity of the parts. They all look the same. They're all machined the same. In this business, a part that looks different from another part is a huge red flag. Like, why does this look this way? Actually, now it's going to rotate over on the other head, and it's going to deburr the windows, we call them, those round kidney-shaped features. It's going to deburr those parts. It's basically just one part. It's just all the operations that we used to have are condensed into these two operations on two heads. We'll remove that part, and then that chuck will traverse in A-axis over and grab this part on this side, pull it out to length, and then we'll cut it off and we start the entire process over again.